But then you eventually subdivide it, get rid of site.
Yeah.
Oh, yeah. Yeah. Bullshit. Yeah, it's true.
All right. So we'll be able to finish mixtures today. So where were we? We were looking at okay. So we looked at the situation where your volume in the tank is not changing. That's going to happen if your inflow volume and your outflow volume are equal. So equal amount coming in, equal amount coming out. But if you had an case where your inflow is twice the rate of your outflow, so this is 10 meters cubed per second versus 5 meters per cubic second, then suppose like there's this much water in here and the tank is big enough to hold more water, then your volume of water will progressively grow at a rate of a net gain of 5 cubic meters every second because you're putting in 10 and taking out 5. And that means that your outflow rate of pollutant or salt or whatever is going to be flow times the concentration, but that concentration is always amount over volume, but that volume is not constant anymore. It's 5T plus 100. And your inflow, which is your orange, that's fixed. So that's like, you know, we have much more control over that because you're just setting the concentration to be some diluted 0.1 grams per meter cubed coming in at 10 meters cubed per second. But you're then that water goes in, it gets mixed, and then what comes out is just some concentration that's after it's been mixed. So you don't know what that is. It's just going to be amount at that time divided by the volume at that time. And the equation ends up becoming like this green equation, which is the fundamental, what is it? The law of conservation of matter is going to become this with you when you plug in these the orange inflow and the purple outflow. But the issue is that because your volume is non-constant, your coefficient in front of this Q is not constant anymore. So you'll have to use the integrating factor method because it's not constant. Well, why don't let's suppose if you didn't realize that it had to be in the integrating factor, let's just take this equation and then see what happens if you had by mistake tried to use the method of undetermined coefficients. So this way I'll make it very clear that the method of undetermined coefficients should not be used when this thing is not a constant. So this is a non-constant coefficient in front of the Q. You know you have to use the integrating factor. But suppose you, by mistake, decided to use the method of undetermined coefficients. So the method of undetermined coefficients says that you're going to build the particular solution. And for this one, what would you, even though we know it's not the right method to use, if you thought you could use it, what would your particular solution form be? Yeah, it'd be a constant because you always read off from the right-hand side. So let's say it's a constant. And then we're going to assume that it's some constant A. But because we're assuming it's a constant A, we'll try to plug it in. Again, we assumed that A is a constant, means that the derivative of Q is going to be 0. Plus, then you plug in this is here. And then you're going to plug in the Q is A. So you just have A out here multiplied to this is equal to 1. Okay, and then you might think, well, it looks like we can use it because we can solve for A here. We don't get any kind of false statement or anything. We just have to solve for A. Of course, this 0, you don't have to worry, imagine the 0 is not there. Then you just multiply both sides by this T plus 20. And you might think that, oh, we have no problems because we were able to solve for this capital A. I think I mentioned this before, but this A here is not a constant. It's T plus 20. But we assumed it was a constant when we plugged it in. So it's like how did we even get this 0 here? We got this 0 after plugging into the differential equation because we assumed that A is a constant. And then we end up getting an answer that's not a constant, but you can't have it both ways. You can't be like, I assume that it's a constant, but then I don't get a constant. You're like, okay, well, I guess it's not a constant. That is a contradiction, right? We went in assuming that A is a constant in order to plug it in. And then using that assumption, we solved for A, but then got a non-constant solution for A. And that's inconsistent. We would have, yeah, it's inconsistent with the original assumption that A is a constant. We would have not gotten 0 here if we didn't assume that A was a constant. On top of that, let's check. So let's check if this is actually a particular solution. So if we said Q of P is equal to 10 plus 20, let's say, okay, well, why don't we just even make sure that this actually works? If we took the derivative of Q when it's T plus 20, dQ dt would equal 1, right? Plus, then there's the 1 over T plus 20. And then you were assuming that Q is T plus 20, so we're going to multiply this by T plus 20. And this should equal 1. Well, you get 1 plus, this is T plus 20 over T plus 20, which that's the same on the numerator and denominator, so that's just 1. And we get that 2 is equal to 1, but this is false. So this is not a solution to this differential equation. This is not a particular solution to this differential equation. We don't have any expectation that this would be the solution because this was basically assuming that A is a constant and then plugging it in, getting this 0 here, and then we ended up solving for it and getting that A is not a constant, and that's inconsistent with the assumption we had. And yes, it would have solved this differential equation if we could get this first term, right? So I'll just circle it in purple and say if we could have somehow assumed that this first term would have been 0, but that would have happened only if A was constant. And so you can't have it both ways. You can't be like A is a constant, but then later we discovered that A is not a constant. And you could take this and plug it into the differential equation and get 2 equals 1, and that clearly doesn't solve the differential equation. So this is showing you that when you have a non-constant coefficient in front of this Q, you need to use the integrating factor. And so this is the process. You just take the P of T is this 1 over T plus 20 that goes into this formula for the integrating factor. You can drop the absolute values and the plus C's and just get this T plus 20. That gets multiplied to both sides, assuming you calculated that correctly. The left-hand side should be the derivative of the product of U times the unknown Q. Oftentimes in the past, that Q was an X. Then you also integrate the right-hand side. Then the derivative and the integral on the left-hand side undo each other. And then you have Q that's possible to isolate really easily now because you just divide both sides by T plus 20. And then you'll end up getting the Q of T as a function of time. You plug in the initial condition. So the initial condition is that at the time equals 0, the amount of salt is 100. That's going to give you C is equal to 2,000 going in here. If you wanted the concentration, it's going to be the Q of T divided by the V of T, the V of T being the 5T plus 100. And so you'll have the T plus 20, and then you'll have that multiplied by 5 times 5T plus 100. But I just factored the 5 out so that if you factor the 5 out of this 5T, it'll be T plus 20. And then there's another one of those down here. So that's why that's squared. This graph is showing you the amount of salt in the tank as you progress in time. Initially, there's 100. So this red underlying thing is showing you that there's 100 grams of salt in the tank initially. As you pump this diluted water in, and then you're pumping in at twice the speed you're pumping out, but even then you're pumping in diluted water while some more concentrated liquid is leaving, even though it's leaving slower than the diluted coming in. Actually, it's probably the reason that the dilute is coming in much faster is probably making this amount of salt go down much faster. But then at some point, the amount of salt is starting to increase instead of decrease. And that's because you're just increasing in volume, so you're just adding like 5 cubic meters of liquid with diluted salt in there, but you're just adding that forever. So you're just, starting at 100 cubic meters of liquid, which was more concentrated. Now you're just getting more and more liquid in there. It's more diluted, but you're still getting, if you were to evaporate the water and just figure out how much salt is actually in there, there is actually more in there because you're just adding, what is it? If you're pushing in 0.1 grams per meter cubed, 10 meters cubed per second. But some of it's coming out. So you're kind of adding a net of like half a gram per second of salt in there forever. And that's why, yeah, if you're assuming this tank is infinitely large, it's going to become like 100, 200, 300, 500, 600, 1,000 cubic meters of more diluted, but you still have more salt. If you were to just evaporate out the salt, there's still actually more salt in there. And that's why this red graph keeps growing forever beyond the initial amount. The initial amount is this green dotted line, which is the 100 grams of salt in there. So initially there was a concentration of 1 grams per meter cubed of 100 cubic meters of water. So that was 100 times 1. So that was 100 grams of was in there. So that's the concentration the graph for concentration I didn't do, but it'll look kind of like this. It'll look like it's just going to get diluted. Even though there's a lot more liquid in there, it's still going to have a lower it's just going to plateau to a concentration of 0.1. Okay, now let's say that the size of the tank is not infinite. So let me just duplicate this page because I feel like I'll need more space. So let me copy and paste this page. And then let me clear this. Okay, so say the size of the tank is 100 cubic meters. And when it's full, there's an overflow valve at the top that just discharges the excess liquid. So this is like if you were in a bathtub and you let the water like go up and up and up. And let's say your drain is kind of clogged, so like it can't keep up with the faucet. Then after a while, it's going to, usually on a bathtub, there's like a little hole like at the top so that like it can like just eat up all the excess liquid. Or if you don't, then I guess it'll just flood your bathroom. But if you're thinking about that, that's like the overflow valve. So your faucet might be adding water faster than the drain can actually handle. Your volume of the water in the bathtub will go up, but then there's a limit. At the top, it'll just overflow into some overflow valve, or it'll just go into your bathroom floor. And so let's say that's what's going on here. How long, so this first question is super easy. How long will it take until the tank will overflow? What would be the differential equation that describes the rate of change of the amount of salt in the tank from after it overflows, from this moment onwards, and determine the function as a function of time? So we know that it's the same situation as up here. So the volume is going to still be 5t plus 100 because you're just adding, 5 net cubic meters per second. So your volume is still going to be this from before. And then the question is, if the size of the tank is 1,000, when will it overflow? You're just interested in finding a time when the volume becomes 1,000. So it's going to be 1,000 equals 5t plus 100. And so you'll subtract 100, which is going to make it 900. It's equal to 5t. And then you can just divide. And if you do that, then you'll end up getting that t is equal to 180 seconds, I think. Yeah. So that's the time when it overflows. Overflow time. Like when it overflows. Now I want to, so before it overflows, we already have the solution. This is what's going to happen before it overflows. Because before it overflows, your volume is just changing at this rate. And we've already solved that problem. Now the question is, can you figure out what's the amount of salt and the concentration after it overflows? So you want to write the differential equation for when it for like at 180 and onwards. So let's look at like the situation when, again, when t is greater than or equal to, well, greater than 180 seconds. That situation, let's look at the picture. So the picture is going to be essentially the same as this picture right here. So I'll just copy and paste this. But the what's going on is that the water is just gonna overflow after it gets to the top. The drain is still going out at 5 cubic meters per second. The inflow is still 10 cubic meters per second. And then after 180 seconds, it's gonna all discharge on the top. You're gonna still use the same differential equation, which is this one right here, but you're gonna have to recompute terms in it. So this is the same thing we're gonna have. But so dq going in, is that going to change or stay the same? This is just, we're still continuing to pump this forever like this. So basically your concentration and the volume going in for the dq in is not changing. So I'll just use this. So that's not changing because we're not, the only thing that's changing is the outflow. So we have, this is not changing. Let's grab the outflow of stuff. Let's just take all of it. Let's see. This was what we had before. Before it overflowed, we said that, well, it's going out at 5 cubic meters per second, and the actual amount of the concentration is the amount at that time divided by the volume. And let's just delete the rest of this. Let's see. Okay, so this is what we had before. Okay, when it overflows, so that's like when t is greater than 180 seconds, that means the water had made it to the top and it's just anything extra is just going out from that point. Is the if you look at the total outflow, is it still 5 if we're also letting things pour out from the top? What is it going to be? 10. Good. So this will be 10. I'm going to write it in red so that it's clear that this changed from before. This is 10 because basically all the water that is being pumped in, 10 cubic meters per second, only 5 cubic meters per second was getting out of this like clogged drain. But once it makes it to the top, all the additional 5 cubic meters is also just going to pour out at that point. And so what's going to happen is this tank is not going to hold any more water. It's going to just push all the water that comes in is just going to all flow out, either down here or on the top. So the total 10 cubic meters per second is all going out at that point. Then the question, okay, so we don't still know how much salt there is at that time in the tank, but we can say something about the volume. After it overflows, so when t is greater than 180 seconds, what's the volume of liquid in the tank going to be? It's going to be 1,000. It's not growing anymore. These are the two changes that we have to make from the previous, like before it overflowed to after it overflowed, right? After it overflowed, now all the water is just leaving. And the volume is just going to be fixed to 1,000 because the tank is just letting it all go out. So this is actually an easier problem because we don't have we have a constant volume. So the differential equation ends up becoming dq over dt is equal to, this is still 1 because it's going to be this right here. And then it's going to be minus this 10 and this 1000 just divides out to 1 over 100 times q. So this is our differential equation now. It's for when t is greater than 180, right? So it's when t is greater than 180. This is when we're already overflowing. This is you could write in the standard form. You're just going to add the 1 over 100 and make this equal to 1. But this is a constant, you know, so this right here is 1 over 100. This is a constant. So you can use the method of undetermined coefficients. You could also use the integrating factor too. You know, integrating factor is arguably more powerful because it works all the time, no matter what, both for non-constant and constant coefficient. But people find that it's more cumbersome because you have to take an integral. Versus the method of undetermined coefficients trades integration with algebra. The right-hand side is 1, so your particular solution form would be some constant a. dq over dt for a constant is 0, plus you'll have 1 over 100 times the a has to equal 1. This means that your a has to equal 100. And your homogeneous solution is easy to read because it's just looking at the coefficient in front of the q. So your I'm gonna label this as Q2, Q1 being like before it overflowed, and Q2 being like the salt concentration after overflow. And it's gonna be the 100, which is the particular solution we just found, plus the C times the negative of this 1 over 100, which is going to be, no, actually, it's the negative of this 1 over 100 right here, so it's gonna be negative T over 100. So this is like your particular unhomogeneous solution. And I'll just use colors again, like I always do. This is purple, and this is a homogeneous solution. And that's after it overflowed. So I'll just make a note here, and this is like the previous page we found when it was before it overflowed, but this is when t is greater than 180. It's going to give you this solution. Let's look at the solution we had before. This was the solution we had before for when before it overflowed. So let me just move this over. This is from the previous page, which was before it overflowed. Let me just delete all this. We said that C was 2000, so I'll just write that in. So this was like Q1, and I'll label that this one right here is going to be for when T is 0 to 180. Because the previous one, we just said, okay, we're just pumping in twice as fast as we're pumping out. And we assumed that it was an infinitely large tank, but now we're not. We're just going to say that 1,000 cubic meters is the size of the tank. So it can do this solution until 180 seconds. And then after 180 seconds, you have to come up with a new equation because the volume is not changing after that. And the outflow, the discharge, is actually equal to the inflow, which is 10. And so you have these two separate solutions. You have Q1 for before 180 seconds, and then this Q2 for after 180 seconds. This one's actually like a rational function, and this one's an exponential decay term right here. And so you have some fundamentally different physics going. Well, the physics is still the same. It's conservation of matter, but the solution form looks different. But there is a C here that is with the second solution. That's like after it overflowed. The question is, how do I find this C? So there was also a C in the previous one, which was this C right here. And I said that it was 2000 after you plug in this initial condition, which is saying how much salt there was at initial time. For this C, you don't want to plug in that same initial condition because this solution doesn't actually is not relevant for t equals 0. This solution is only for t is greater than 180 seconds. Does anybody have an idea like how you might find the C for this one? Yeah, so yeah, exactly. You want to make sure that whatever salt you had in it, like, so this is just modeling the salt for the first 180 seconds. And then there's some amount of salt in there right at 180 seconds. This should pick up from there because you can't have salt suddenly appear or disappear. So you're like, this is just saying, okay, this is how the salt is evolved, how much salt is, what this is the function, the salt is a function of time before 180 seconds. There's going to be a certain amount of salt at 180 seconds. And this has to pick up from there because otherwise it'll look like you have salt that suddenly appeared or disappeared. So what does that mean? That means that you need to have this happen. So you're going to say Q1 is going to have some amount of salt. So I'll just say that from this, you're going to get that Q1 at 180 seconds. And then that has to match with the other, this one is for when t is greater than 180 seconds, and that has to match with the salt. So this is modeling the salt between 0 and 180 seconds in the tank. This is modeling after 180 seconds, but they need to match up right at 180 seconds because this is just saying like we're adding salt. You know, there's some net gain of salt because basically this red line is going up. And then we need to, so this is like an exponential decay. So let's just sort of graphically think about what this might mean. This means that let's suppose that you have, I'll just underline this in blue and say like this right here is for when t is greater than 180 seconds. So the first one is going to have, we already saw the kind of graph it was kind of like this. And then right at 180 seconds, we know it's going to overflow. The way this graph looks like it's like an exponential decay. So I'm going to think that it's going to probably decay after this. But you don't want the thing to just be like this, like, because then right at 180 seconds, it looks like salt just suddenly magically appeared in the tank. Or you don't want this either because then it'll look like the salt magically disappeared in that split second. It just picks up where it left off. And that's going to be this condition that the Q1, which is the red graph, and the Q2, which is the blue graph, have to meet there. It's like a continuity condition. Salt can't suddenly appear or disappear in the tank. So if you plug in 180 into this, that means you're plugging in 180 into all the t's here. That's just an exercise in putting it in your calculator, but you get 109 if you do that. And so you get 109, and then you get this is equal to, right here, you're also plugging in 180. So this will be like 100 plus c times e to the negative 180 over 100. That's like the 180 goes up there. So if you solve for c, you just subtract both sides by 100. And then you multiply by e to the, so you'll just get 9, because if you subtract by 100, and then you're going to multiply by e to the positive 180 over 100. And so that's the c. I mean, I guess the 180 over 100 could be simplified to 9 over 5 or something. So once you have that c, that goes into this c right here. And we've got our full solution. So we've got our Q of 2. T is equal to 100 plus this 9 times this thing times there's this e to the negative t. over 100. This does simplify though, so I'll just write it in simplified form. So this right here is like 100 plus the 9. They both have the same base. It's like these two can be added together, so it'll be like this. Let's just shift this down. So it'll be like this 180 minus t over 100. This will be after it overflowed. So like this graph will be like this piece right here. And then of course this graph was from before. It's gonna look kind of like that piece right there. Then the C here that we found, this blue one, is guaranteeing that they will be continuous right at 180. So you're not like having salt suddenly appear or disappear in the tank right when it overflows. So I'll just say salt does not magically appear or disappear at equals 180. That's what this condition is ensuring. So so this is a case where you're having a tank that's big enough to hold more water. You have an initial amount of 100 cubic meters of water. You're pumping in water faster than you're pumping out. The water you pump in is more diluted than the original concentration of the water in the tank. And then you're letting that, net surplus of water accumulate, net surplus of diluted water accumulate in the tank up until it hits the capacity of the tank where it starts to overflow from that point. And so you have a piecewise function where the first part of the solution is going to be described by a differential equation of this form, which is the non-constant coefficient differential equation, which requires using the integrating factor because we did the method of undetermined coefficients and got some statement like 2 equals 1, which is not true. So that one, because you have a non-constant coefficient of Q, that's going to be good for if you're just assuming this tank is infinitely large. But then if we're going to cap the capacity of the tank to 1,000 cubic meters, then right at that point, your inflow is still going to be the same because you're just letting that just pump in forever. But your outflow has changed significantly because you're now not allowing the tank to hold any more liquid. It's just going to discharge all the extra liquid. So that's why the outflow becomes 10, just like the inflow. And then at that point, your volume of the tank, liquid in the tank is fixed to 1,000. That's not going to require using the integrating factor because you have a constant coefficient of the Q. You could use a method of undetermined coefficients. You'll get like your particular solution and your homogeneous solution. Your homogeneous solution will be what you read off from just looking at the differential equation. You get this negative t over 100, which is an exponential decay term. But you want to make sure that even though we know it's going to decay, you want it to start where the amount of salt was at 180 seconds from the first equation, so that you're not magically creating or destroying salt instantly. And so the solution is going to look like this, which we basically, this red graph is the same as this one. So this one is assuming that you have an infinitely large tank, then you're just pumping in more and more diluted liquid, but basically the diluted liquid carries some amount of salt. So basically your salt is always going to grow up forever. But let's say at 180 seconds, it's going to not hold any more liquid anymore. So that's why you see a break in the graph. This is actually 200 right here. So you see like around 180, there is something that happens where the dotted line is to show what would have happened if the tank was infinitely large. But since we're letting it not be, you're going to discharge all the extra liquid coming in. And the blue graph is the same graph that we had gotten right here, but it's going to connect right where the red graph left off. So why don't I just copy and paste all of these solutions? So basically, the red graph is this. The blue graph is this one. So maybe I'll use colors. So I'll just say that this right here is the red graph. This right here is the blue graph. And we're just saying that this is going to be a piecewise function now, where this red graph is for 0 to 180. This blue graph is for greater than 180. Okay, so that's the solutions we had before. The graph below is concentration. So here was like you have 100 grams of salt in the tank, but there was 100 cubic meters. So if you like just divide 100 by 100, you get 1. So the concentration is 1 initially, and then it'll just go down when you put in diluted water. And if you can't probably see this very well, but like there is also like a blue line right here, because I wanted to just, take the concentration and also the concentration after it overflowed. So we already found the concentration for before it overflows, right? That was up here. Let's see here. It's this one right here. So this was like when we did it before. So I took this and grabbed it, but let's grab this one too. So this one goes down here. So this is the red graph. It's the concentration for before it overflowed. So do C1. Let's just do this. So this is C1 of T, which is equal to Q1 of T. Divided by the volume was 5T plus 100. Before it overflowed, it was just, growing volume like this. Then the blue one is going to be the concentration after it overflowed. It's going to be the amount of the salt in the tank after it overflowed. So instead of Q1, it'll be Q2 divided by what was the volume? 1,000. So that means that you're just going to take this right here and just divide it by 1,000. So just copy and paste this. So you have piecewise function for the concentration where these are the same domains. So you have like the first one is for between 0 and 180, the other one's after 180. All you're doing is you're taking these two solutions and dividing by the volume, but the volume for the first one is actually changing with time, so that's why it's 5T plus 100. The other one is just fixed to 1,000. And if you actually, you're welcome to check this on your own, but if you graph these, they will be these graphs. There's a tiny bit of blue here that's like hugging the green, so it's hard to see that. But it turns out that continuity in the Q will also ensure continuity in the C. The green dotted line here is like just showing you, well, this one's showing you the initial amount of salt. This one's showing you 0, 0.1. Okay, so this is just saying like concentration of 0.1, which is actually the concentration of the inflow, right? So like the thing that's being pumped in is actually 0.1 grams per meter cubed. So what's going on here is that you have a tank that's full of salt at a concentration of 1 grams per meter cubed, which is 10 times more concentrated than the 0.1 grams per meter cubed of the inflow water. You're pumping in water faster than you're pumping out. So essentially it's going to recycle this, but basically at first it's like the volume of the liquid is going up. But then when it overflows, it's for sure just going to be like a case where it's just recycling the water. So it's like basically you're just discharging all the water that's coming in, and the water that's coming in is a fixed concentration 0.1. So in as you go forward in time, you wouldn't expect, even the blue solution to go below the 0.1, because at that point you're just recycling the water back to the diluted water. So, yeah, I don't know if there's anything else I wanted to say. I think I'm good with, so we've covered the amount. I mean, there's more, in the textbook. They look at like, um, multi-tank, systems and things, but, I think this is enough for us. So we'll just have, these types of mixture problems. One where you just have inflow and outflow is the fixed, so then you're always a constant volume in the tank. The other one where your inflow and outflow are not the same. In this case, we decided that the inflow was faster than the outflow. And then that was nice because because you could have it the other way too. You could have outflow faster than the inflow. But when you make the inflow faster than the outflow, your tank's liquid is not going down but going up. And then I can also give you another case where it now overflows. And then that's a different situation. And you can see that there's some kind of big event happening right at 180 seconds. The C graph, it's hard to see anything happening, but with the Q graph, you can clearly see that there is some kind of shock in the system, which is basically I'm used to be pumping water out at 5 cubic meters per second, but suddenly because it's overflowing, it's now we're losing water at the same rate I'm coming in. And then that's a very abrupt change though. Right when it like overflows, it's like bam, it used to be flowing out at 5 cubic meters per second, but now it's 10 cubic meters per second. And it's interesting to see that the Q solution actually, although we made sure that it was continuous there so that you're not having salt magically appear or disappear, it's not differentiable at that point. There's like a kink in the graph. Yes. Yeah, so we'll do our test on Monday. And this is the last thing that's covered. So we're gonna like probably not talk about this because we only have 2 minutes, but it's up to all of chapter one. Well, we didn't cover every section in chapter one because there's like existence and uniqueness and direction fields and Euler's method. So I skipped some sections in chapter one, but all the sections we did cover in chapter one is going to be on our test next week. And then chapter two is, as you can see, there's a d2x dt2 squared. This is just the second derivative term that's added to our differential equation. So this is the second order. That's why you see second order here. So all the first tests will be first order equations. And so that's all we've been doing is first order equations. We were solving it using antiderivative or separation or integrating factor and method of undetermined coefficients. And then we had various applications like exponential growth, decay, Newton's law, cooling or heating, and then mixture problems. So your test will be like solving differential equations, and then there'll be word problems. So you should have a bunch of problems to just solve differential equations, and then there'll be like word problems. But on the calendar, I have it as like there's a part one and a part two, just because when I write the test, I'll make a decision of whether it would be best to just have you. So the first day might be just solving differential equations and maybe just one word problem, like maybe exponential decay or growth. And then the second day could be Newton's law, cooling, and mixtures, because if you had all of that in 50 minutes, maybe it might be too hard. And then the second day, I think we could just do a half class period for tests, because it would just be like two problems. Unless I can make the test short enough that I think you can reasonably do in 15 minutes. But I don't want you guys to be pushed too hard. And you can write, I'll send an email out, but you can bring a one piece of paper front and back with anything written on it. So it could be like your formulas, or it could be like a worked out example. Like you might just like do an integrating factor example and a method of undetermined example or a mixture example, so that you can see that as a reference, as a template to doing the problem. You can write literally, I'm not going to police what you write on that, but you can bring whatever you want, one page front and back. I'll send an email out just in case people are not here to hear that. And the office hours this week, like I can like just present problems that are going to be similar to the tests, so you guys can like come to those so that you can get a heads up of what kind of problems. If you're looking for problems to do, obviously the homework and the daily practices are all good problems, but they're all basically problems from the textbook that I selected. And there are tons of other problems. If you just like if you notice the homework, you're just doing some of them, but just do the other ones too if you want, in the same sort of near the problems that I assigned. And the odd ones have answers in the back. So even though they're not fully worked out solutions, you're probably not gonna get the same, like if it's like 47.6, you probably wouldn't have gotten that unless you did it correctly. So maybe just prioritize doing problems in the back of the text, in the end of each section where I'm assigning problems. Do like some of the odd ones that are similar to the ones I assigned. I just can't assign all of them, so you're free to choose those, and then that way you can check in the back to see if you at least got the answer correct. Yeah, so just yeah, good luck with that, and we'll just keep moving. Next class period, we'll move on to second order. That won't get covered on the test, but the next test after.